Hey, okay, so now I'm gonna finally make predictions. So and actually, sorry, I forgot. I actually finished the neural network model. So all I did is I initialized my parameters. I did that a few videos ago. For propagation, I did that a few videos ago. And for my cost, I just retrieved the A2 that forward propagation gives right here, right? So forward propagation returns A2. I took that A2, I passed it into cost and my Y training values, and obviously compute cost takes those arguments, it returns my cost, right? And then my gradients, right? So the gradients of my W of my weights, my biases, that's equal to this my backwards propagation, right, which returns those values, and it takes these arguments, and I just pass those in right here, and then my optimized parameters, um, it just takes parameters, grads, and learning rate, and gradients. Obviously, I retrieve them from the backward propagation, and my parameters is just the original parameters. And I pass in a learning rate of 0.05. I'll put this to 0.01 just so we can play around with it. And I'm going to print this a little bit and show you what this looks like, right? So there's that. Now, if I do like a higher learning rate, you see we're actually getting better and better, closer to that gradient, right? So 0 point up, and actually that's that is not, so let's try 0.9 maybe. So it's okay. We can try we can try different numbers. We can try 0.7. We can try 0. Okay, I have no idea why I just opened Windows. But we can try like 0.8. And okay, 0.8 is terrible. 0.7, well, it's not terrible, but you get the point, right? So we're getting closer and closer, right? And this always depends on your model. It depends on your neural network, your data, whatever. So 0.7, maybe let's try that. Okay, let's try 0.01 or something. Let's try 0.05. Okay, I forgot to close my parentheses. Let's try 0.05, and let's try, I guess, let's maybe try 0.07. Let's see where that gets us. So, not too well. So, 0.06 maybe? No, 0.04. And I guess 0.04 is fine to stick with, but as you can see, our cost started at 0.69, and we go down and down and down and down and down, right? And now I'm gonna make a prediction. So we want to actually check the accuracy um, of our model, right? So parameters, we're gonna take parameters as an argument, and what's it called? We're gonna obviously take x as an argument, right? And you can call this test x, whatever you want. I'm gonna call it test x. And we need to actually retrieve our updated parameters. Um, and what's it called? La, 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 la. My brain isn't working. Completely shut off. Okay. All right. So for parameters, let me think. We want to pass in the updated parameters, right? So first, pass updated parameters, right? And then make prediction. And so we need to forward propagate to make that prediction, right? So actually, I'm gonna make a test x equals numpy array. And I'm just gonna make this like one number. I'm gonna do, let's say, 18, right? Something that's for sure gonna be 1, because if you remember, as our numbers go up, our predictions become 1, right? So 18, it should return in a y, right? So I'm gonna say params is equal to, and here I'm just gonna return my Uh, all right, actually, let me say, you know what? I may as well. Yeah. So you know what I'll say? I say params is equal to. I'll just say cash. Cash is equal to. Let me bring this laptop. I'm gonna crouch like a. Okay. So param is equal to W1. Forgot to put that in. Yeah. So W1 and params W1, right? Because this is gonna be fully updated by the time we retrieve it here, right? Because the for loop is gonna be done, right? So W2 is to params W2. I have no idea why I did a dictionary, but yeah, just ignore that. I'm just gonna say, and actually, I just realized something. I think we can just return. Wait, there's no way. I think we can just return optimized params. That's fucking okay. That's crazy. So model is equal to that, and maybe we can just retrieve it from model, right? So we can say params is equal to model. Maybe. I'm not sure because optimized params is returning what? It's returning. You know what? I do not think we can do that. Okay, this is terrible, right? So cache. Yeah. So let's just try it again. So B1 params B1 and W2 or oops, I meant B2. It's out of order. Sorry. Params B2. Okay, and let me try returning my cache. And params is gonna equal to model, right? Or neural network model. So that's still called test. Okay, it's gonna equal test. Sorry. Let's just call this model. Yeah. So model is gonna equal to model, and then I'm just gonna forward propagate, right? So I'm gonna forward propagate, and what arguments does forward propagate take? It takes all of these, right? So let's put these in here. Okay. I copied the entire function apparently. So it takes W1, right? It takes all these. So I'm just gonna say params W1. I'm gonna say params. What the fuck? Okay. Params B1. And then params W2. And then params B2. And I'm gonna pass in my test X here. And I'm gonna say prediction is equal to that. I'm just gonna go ahead and return my prediction. Right. Okay. Yeah. And I have no idea why I'm taking this as an argument. We don't actually need to take that as an argument because we're doing that here. So I'm gonna try that now. So y hat is equal to predict. And I also have no idea why I'm taking this as an argument. Wait a minute. Param. Yeah, okay. I have no idea why I'm taking that as an argument. So uh yeah, I don't know what I'm doing. So we can just get rid of that. I have no idea why I did that. And there is an error somewhere. And I have no idea where because it's not really telling me. That's weird. Okay, I'll run it and I'll see what the error is. So y hat equals that, and then I'm just gonna print y hat and see what the error is. Okay. Yep. I have no idea why I did that. Okay. And we're just gonna try that. Whoa. Okay. What in the fuck? Print y hat a2. Sorry. Get rid of all that bullshit. Okay. So 0 point. I believe that's our prediction. I have no idea what I'm doing. So I'm gonna say a2, right? So I don't have to do all this over here. Yeah. Sorry. So we'll just return a single thing out of there. Why is it printing the entire Earth? Wait a minute. That's why. Okay. Oops. My bad. My bad. My bad. My bad. My bad. My bad. Wait a minute. Print cost, and then am I printing my forward propagation or something? Return prediction A2. Why is it printing my W1? I have no idea why it's printing that. Y hat is equal to prediction y hat. Why is it doing that? It's lucky annoying as fuck. Wow. Okay, I cannot believe this. This is actually the weirdest thing ever. Because I'm returning cash here, but I'm only predicting. Wait, prediction is equal to this. What the fuck? Return? Am I printing something? Oh, I'm printing my model. Okay, okay, okay. Print. Okay, that's not good. Mm, okay. Shit. This is why. You know what? We'll just remove this, right? Because we know our cost is working fine, right? We're going down. So let me try this. There you go. Okay. So 0 0.9, right? 18 is obviously going to be 1. So I'm going to put something absurd. I'm going to put like 3 in there, right? And 3 is definitely going to be a 0, right? Because 3, you see, these are all zeros over here. So I'm going to delete this. I'm going to run it again, right? You see 0.003, right? So what if I do 9, right? Something in like the 50th percentile. Something that's like 50-50, right? So you see 0 0.4. Okay, I'm back. So just to show, this is the perfect learning rate I got for this model. It's literally close to perfect, right? And 1,000 iterations. And I want to talk about a few problems in this. So obviously this is just an example. It's not that serious, right? But you see our x is actually varying from 1 to 17, right? So that's really bad because now our gradient has to take like a million different steps. It's just all over the place, right? So and actually I'll demonstrate that in a second. But one thing we could do is normalize our data. So we could lower the variance instead of going from a really low number to a high number. Normalizing could actually could make our variance between 0 to 1, right? Or nothing too much lower than 0 and nothing too much higher than 1, right? And that's basically going to lower our variance, and I'm going to show why that's good in a second. But I'm not going to get into doing that at all, right? Now that's for another playlist. But yeah, so one thing you want to do is normalize your data if you also have some absurd learning rate. Like this is pretty absurd, right? Finding a perfect learning rate like this. And also it can vary, right? As our data gets bigger, our perfect learning rate is going to change. But I just want to show this right now. So if I run the code, you see our gradient descent is not going back and forth, right? It's getting smaller and smaller and smaller and smaller, right? Boom, 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 boom. And 9, it says 9 has a 40% chance of being 1. And as you can see, that's kind of accurate, right? It's not super because 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, that does kind of make sense. Um 10, 11, 12, 13, 14, 15, 16, 17. So not okay. So I guess it's not super accurate because in reality this should have been closer to 50%, right? Uh, and I have no idea why I get an error now. Very odd. So let me try running it again. There you go. Right, and it's actually getting worse. So maybe 38 is a better number, right? Or maybe 36 or something. Okay, nope. So maybe 39. Right, but I just want to show you like what it looks like when you keep playing around with this, right? So if I do like 41 or something, and you see I'm actually getting very close to that number, right down here. If you look, getting very close to that zero. And our prediction says 40%, right? And if we go to that 10 threshold, we'll get to 65%, right? Again, this isn't really good data, right? But if I do like 15, or let's just say 14, for instance, if I do 14, right, it should give me like a high number, right? 97% chance it's a 1. And I'll do 14 and I'll do like 4. So one should be high, one should be low, right? You see 0.006. And I believe this is kind of like overfitting the data because, again, this is terrible data, right? But that's the point. Okay, so I kind of want to explain what that does. So normalizing our data, right? It makes our inputs be between 0 and 1. So if our inputs vary a lot, right, and we have a gradient descent, and this is not gonna work too well with a 2D demonstration, right? Because it doesn't make sense. This is multi-dimensional, right? But let's say we have a two. Let's say it's two-dimensional, right? And like that. So our gradient descent, right? It's gonna we want to get closer and closer to that zero, right? But the problem is our gradient is kind of just pretend this line is going through zero, right? Our gradient is and pretend this is 3D, right? It's obviously not 3D, but pretend this is 3D. Um, and the problem is our gradient at higher variances, right? It has to take a bunch of steps to get to zero, right? And at lower variances, it has to take obviously a bunch of steps to get to zero, right? So gradient descent is kind of all over the place. Now, let me go back. What normalizing data is gonna do is our gradient is gonna be kind of like this, right? Right. So our gradient is not gonna have to go back and forth over and over again. Instead, if it starts like let's say at around here, all it has to do is go to the center, just a one-way path to get to zero, right? While as opposed to this, right, gradient descent has to go back and forth, high variance, low variance, right? But this ensures our variance is between 0 and 1. So even if we get a really high number, chances are it's not going to be much higher than 1.2. And I have no idea why I'm writing with green, but that doesn't matter, right? So it's going to be like, let's say 0.2, and the lowest is going to be is like 0.3 or something, right? Depends on the data you're working with, of course. But this is gonna stop it from taking a million steps, and it's gonna start at like 0 or 1, just a straight path down to our zero gradient descent.